Welcome to today's webinar brought to you by Bruker Optics and Netsch Instruments, entitled Tips and Tricks to Evaluate Complex Gas Mixtures Evolved During Thermo-Decomposition. We have two speakers today. Our first speaker is Sergey Shilov. Sergey Shilov is an R&D manager in North America at Bruker Optics. Sergey joined Bruker in 2001. He is responsible for the support and development of new applications for the Bruker Research FTIR systems. He received his PhD in 1992 from the Russian Academy of Sciences in polymer physics and his master's degree from St. Petersburg State University in Russia in physics in 1986. The Alexander von Humboldt Foundation in Germany awarded him research fellowship in 1996. Sergey published 37 papers in peer-reviewed journals. His research interests include time-resolved FTIR spectroscopy, surface analysis, polymer, and life science applications. Our second speaker is Mike Hsu. Mike Hsu is a senior application scientist at Netsch Instruments in North America and has over 14 years of experience in materials science, with 7 of those years being at Netsch. Mike specializes in thermogravimetric analysis, differential scanning, calorimetry, and simultaneous thermal analysis, as well as coupling these techniques to evolved gas analyzers such as FTIR, MS, and GCMS. If you have questions during the presentation, please submit them via the questions drop-down box located to the right of your screen. We will take some time at the end of the presentation to answer your questions. Now we will begin today's presentation.
So thank you for tuning into our webinar. I'm Mike Hsu, Senior Application Scientist here at Netsch Instruments. And so today I'm going to give a brief talk on TGA coupling with evolved gas analysis with the FTIR. So to give a brief background for those that are unfamiliar with our company, Netsch Instruments produces a wide range of thermal analysis equipment. So now what exactly is thermal analysis? It can be defined as one or a group of techniques that can measure changes as a function of time for material chemistry and physical property changes. So today I'll be giving the short talk with TGA and FTIR. If you're interested in our other thermal analysis that we offer, please check out our website. So for TGA, thermogravimetric analysis. In this technique, we monitor changes to the sample mass as a function of temperature or time. So I have here a simple diagram of how the Netsch TGA system operates. We have a balance sitting at the bottom of our instrument, in which we have a sample carrier connected to the balance where we can then place the sample on top. This design is analogous to a bathroom scale in which you step on it to register a weight or mass reading. Now, as we heat our sample, we can monitor changes to the sample mass and record those temperatures of interest. At the end of a measurement, we can calculate the change in mass, or the delta M, to find out how much sample is left at the end. We can also take the first derivative, in which we denote as the DTG, and this curve shows the mass rate loss of the sample. And so the peaks indicate the temperatures and the times in which the sample is losing mass the fastest. So this information will actually prove useful when we discuss the evolved gas analysis in the coming slides. So another key piece of information that the DTG curve can provide us is it helps us to separate mass loss steps that might be occurring in the sample. So when we first take a look at the TG curve, which is in red, it might look as if there are separate, or if it's a single mass loss event. But when you take a look at the DTG curve, looking at different peaks, it can help us resolve and separate out different steps. So in this particular example, because we have 2 different peaks, we can attribute the TG mass loss as 2 different events. So here are some other properties that we can acquire out of the TGA measurement. So the TGA itself will give us mass changes, the DTG curve, the rate mass changes, but we can also pick out information about thermal stability and the onset of decomposition in certain materials. So some of the applications that can be used with TGA also include looking at oxidative and thermostability of different materials. And with the TGA measurement, if you perform several different measurement runs, you can utilize the information to model different kinetic curves if you then want to change some of the different parameters in your measurements. So here listed are some of the different TGA products that NETCH has to offer. So we have TGA only units, which is the TG209 instrument line. But we also have the STA, which is a simultaneous thermal analyzer, which couples both the TGA and a DSC, or differential scanning calorimetry. So the DSC can measure energetic changes to samples such as melting or sample decomposition, and provides us information on any endothermic or exothermic heats of reaction. However, today our focus will be just with the TGA. So here I have a cross-section of one of our instruments. And as mentioned earlier, we have a top-loading design where our balance sits at the bottom. We can have our purge and protective gases flow through the balance chamber and then up into the sample test chamber. Once it reaches the top, all of the exhaust exits through there. This engineered design also allows the heated gas to have a natural upward rising flow path, and it gives us the ability to seamlessly couple our evolved gas analyzers. So the next question is, why might I need evolved gas analysis? So as you can see, I have a sample of mica in which I've heated to high temperatures. So the TGA curve provides me with information of how much mass loss is occurring, but it only tells me how much mass quantity is lost. It does not tell me anything about what these decomposition products are. Is it water, carbon dioxide, organic volatiles, or something else? Maybe it's a combination of some of these. So this is where we can couple our units to the FTIR. So NETCH has the ability to not only couple with the FTIR, but if also you want to, we can also couple to mass spectrometry or GCMS as well. So in an FTIR measurement, we are looking for different spectras, as each gas species has a unique sort of pattern associated with it. And so here I have just an example of water, in which we know the signal qualities that are produced, and thus we can monitor some of these during the measurement. So when I couple our mica measurement to an FTIR, now I can look at certain different species and then correlate all the different mass loss steps with the individual gas species associated with it. So when I trace the blue curve of water, I see that water is evolving towards the upper end of my TGA mass loss steps. So those incorporated with the 1.9 and the 2.78% mass losses that you see. And then the black curve of carbon dioxide is the second middle mass loss step. So how do we couple our units to the FTIR? So we have a heated adapter that sits right on top of our instrument, and it connects with a heated transfer line, which is the black tube that you see in the middle that goes straight into the FTIR. So in this slide here, I have the cross-section of how all of this integration works. So on the bottom right, we have our TG209 unit, and our sample sits right on top. As our sample decomposes and evolves gases, our purge gases sweep these up to the exhaust at the top, in which we have the heated adapter and the transfer line to then transport these gases to the FTIR detector. Now, it's important to note that we have these adapter and transfer lines heated at high temperature. This is to minimize any condensation and blockage that might occur with our gases, so that these gases can reach the FTIR. So if you wanted to couple with simultaneously with an MS or GC, we have a heated adapter that creates a split so that part of the gas stream goes to the FTIR and part of it goes to the MS unit. But again, the heated is to minimize the risk of blocking and condensation, but it also gives us the enhanced traceability so that we are looking at the gas evolutions at near real time so that there is minimal lag from when they evolve to when they are detected with our FTIR. The second method of coupling is with the other Bruker FTIR unit. So we call it the Perseus, but it's the Bruker Alpha unit. And this particular unit mounts directly on top of the exhaust outlet of our units. And so it eliminates the need for the long transfer line that you saw in the previous slide, coupled to the Bruker FTIR and Venue, which is the benchtop unit. So the cross-section of how this looks is we have a steel short pipe that goes directly into the gas cell of the Alpha unit. And so again, this reduces the lag time between when the sample evolves its gases to when it is read by the FTIR detector. So once we have our units all coupled together, TG with an FTIR, we can incorporate our measurements all together. And during the analysis, one of the curves that we might look at is the Grant-Schmidt, which measures the changes in intensity of the FTIR. So with the TGA curve in green, the black DTG curve, and then the blue Grant-Schmidt curve, we can now look for the areas in which we can now identify what some of our evolved gas analysis can do. So the DTG curve in black will show us where the sample is losing mass the fastest, and usually that also correlates to a peak in the Grant-Schmidt curve. So because we partner with Bruker, so the NETCH TGA curve software and the Bruker's FTIR data can be integrated and superimposed together in both NETCH Proteus analysis and Bruker's Opus software. So it makes analysis much easier for our users. So that will conclude my short introduction to TGA with FTIR coupling. Thank you for your time. And we'll be having a short Q&A at the end of this webinar. So if you have any questions, please feel free to submit them in our webinar's question box, or feel free to email me afterwards. So at this time, I'll turn it over to Sergey, who will continue discussion about FTIR analysis.
Good afternoon, and in this presentation I will give you practical examples how to evaluate gas mixture which has come out from TG. And let's start first of all just to look on the spectra of your gases evolved during TG and figure out do you need a high resolution measurements to collect spectra. First of all, let's take a look at the most common gases like carbon monoxide. If you take a look on the spectrum, you see pretty simple and pretty condensed. Take a look closer. You will see that this spectrum consists of a bunch of individual lines. And these lines deal with so-called rotovibrational states of the molecules. So molecule vibrate and also rotate, and that creates a series of lines. You can see it at 0.5 wave number resolution. So if you reduce resolution and acquire spectrum faster, so you can see that this line disappeared, and we only have a contour of these lines. Okay, and let's take a look on another example. Water vapor. It's also very common in TG analysis. So let's compare 0.5 wave number resolution and 4 wave number resolution. So you can see in case of water, even at 4 wave number resolution, you can see all the series of lines, although they are less amount than compared with 0.5, but still visible. So just you need to keep in mind, if you see a series of such lines, that's mostly these lines related to small molecules, diatomic or triatomic molecules. Very good indications that you have such molecules in a mixture of gases. Now let's take a let's take look on a bigger molecule. Looks like a phenol. So measured 0.5 wave number resolution and measured 4 wave number resolution. You can see there is not actually much changes in the spectrum if you go with a low resolution. The reason of this, that heavy molecules also have rotovibrational structure, but these bands are located so close to each other, so practically the natural bandwidth becomes pretty broad. And you don't need to have a high resolution to collect and identify spectra of heavy molecules. So the idea is, so if you have a mixture of gases, you do not need to collect spectra at high resolution. 4 wave numbers is enough for majority of the spectrum. So let's take a look on a typical composition of the gas phase. This is very typical bands which has come out from TG. You can see here CO2, CO, water, and that's what you can see always come out at the high temperatures. The key point that you also have a CO2, carbon monoxide, and water in the regular atmosphere. So you need to be sure that you exclude atmospheric water, CO2, and carbon monoxide from your measurements. How you can do it? Well, you need to record your background spectrum very carefully. And also you need to purge instrument with say pure nitrogen to remove the contribution of these components. Otherwise, you will be confused between water which is evolved during a reaction and water, atmospheric water is present around the instrument. So these are very simple gases, and they just need to memorize the position of these bands when you do the next step of analysis. So this is a real mixture of gases. It's evolved with one of reactions. And in some cases, it's pretty easy identifiable because these gases absorb radiation in different spectrum ranges. And you don't need to be a guru in spectroscopy to see, to immediately recognize these gases like HF, carbon monoxide, methane, and so on. So if you work a little bit more with TG and look on the spectra, you can easily recognize the position of these bands. You can, without any library search, you can see what kind of gases you have in the spectrum. But that's a pretty simple case. if you have gases which is, well, you will not recognize. So in this case, you will do library search. So in simple case, it's shown here, a spectrum evolved during TG, and this is a spectrum evolved during decomposition of aspirin. And luckily, in this case, this is only one component. And we run spectrum against our library, gas phase library. You can identify as acetic acids. Yes, again, this is a simple case. Let's take a look on more complex scenario. Okay, this is a spectrum evolved during PVC decomposition. As you can easily identify bands due to CO2, bands due to CO, so that's shown in my previous slides. You can see it pretty easily, but question is, what are the bands in below 2000 wave numbers? And there is also a series of these bands about 2500. You can say, okay, there is a series of bands. So it means some small molecules evolved, but which molecules? Okay, let's do investigation. First things, you go to the library search and select the region which is mostly free from the spectra of other gases, which is you can easily identify. So in this case, I select region between 1900 and 837 wave numbers, which is free from CO2, CO, and run library search only on this specific region. Let's take a look on the results. And you can see it comes up pretty close to some of the phthalates. You cannot say what kind of phthalate is this. It can be different types, but at least you know what this is. The composition involves the phthalates. So you can see heat quality for different phthalates is pretty close, 635, 38, 39. So it means you need to maybe further investigation to identify what kind of phthalates is this, but at least you know that you have a phthalate. Okay, well, we only take a look on this part of the spectrum. Let's take a look on the other part. So if you look, yes, this is phthalate bands, but remember we have a series of very sharp bands in the spectrum, which does not come from the phthalate. It comes from something from small molecules, as we discussed before. What we do, we select only the region where this suspicious series of bands appeared and run second library search only on this specific region. So what you see, now there is very good match with hydrogen chloride. Yes, that's as we expected. It should be small molecules. Maybe it's just diatomic molecules, and that's a very perfect match with the hydrogen fluoride. So now you can make a conclusion. So that's a spectrum that's evolved during PVC decomposition. You have phthalates, you have a carbon monoxide, a carbon dioxide, and you have HCl. So you see this that mixture composed of a few gases, and you can identify them. Let's go to more complex example. This is spectrum evolved during decomposition on one of our customer compounds, and take a look on it. So again, you can easily identify this carbon dioxide, carbon monoxide, and also there is a series of bands around 4,000, about 4,000 wave numbers. And when I run the search, I can easily identify the series as HF. So we know now that we have at least 3 gases here, but there is something else present. There is huge bands below 2,000 wave numbers. So what we can do about this, how we can identify these gases. So what I did, I take a look on decomposition on different temperatures at TG curve. And when I move my cursor, I see how the composition change. I figure out that changes of the bands between 2055 and 1028, the ratio of this band changes. So it means it's a ratio of this band changes. So it means you don't have only single component in the mixture. You have at least two components. So, and that's the ratio of these two components changes at different temperatures. So ratio changes, so it means the one component goes up, another component goes down. So let's name these components, component A and B, and figure out what we can do with this. So I extract a spectra at different temperatures. One is 556 and the second is 563 degrees. So both of them is component A plus B, but the different ratios of the components. What I did next, I used spectral subtraction function in our software to minimize one component. So I use A minus B and minimize 1255 band. So then I have a residue. So basically I subtract component B and gonna get component A. So now I play again with a mixture and calculate B minus A and minimize 1028 band. So then I get pure component B. So as you can see, playing with two spectra, I can subtract them, these mixtures, and get spectrum of pure components by just using spectral subtraction. But of course, prerequisites of such measurement, I need to have spectra with different amount of gases in the mixture. Okay, see, I was able to do this and go next step. I run my components and I do a separate library search. And you can see I can identify it. One component is related to carbonyl fluoride, shows on the top slide. And the component B, I also run it and can be identified as a tetrafluorosilane. So you can see this trick allow me to mathematically separate gases and run this separated spectra and identify all the separate gases. So as a result, you can see that's my conclusion. So we have a complex spectrum decomposed with decomposition of this sample. And I can say it consists of the tetrafluorosilane, carbonyl fluoride, and also have a CO2, CO, and also have HF. So you can see even such complex mixture, I was able to identify all the gases which is inside. So this is like way I usually process spectrum, but there is also a simple way it might work. So we have built in so-called mixture analysis in the library search. So this is show the screen of my analysis window for multi-mixture analysis window with a library search. I can select how many components I have in the spectrum and run my library search. So library will try to say, in this case, I set only two components. I assumed to have two components in the mixture. I run library search and software take two spectra in the library and trying to combine them to get good match. So as you can see here, that is a good match. Is a mix. This is a sort of a mixture of compounds. but mostly consist of hydrocarbons, methyl cyclohexane, unsaturated carbons. So you can get at least the idea what it can be inside just using a mixture analysis. So that was before I talk about how to use software search and use some mathematical approach, spectral subtraction to identify different gases. But there is also a hardware approach to analyze a mixture, complex mixture of the gases. So how we can do it? So one of the way doing this is use so-called reduced pressure TGA-IR. So due to reduced pressure, boiling point of compounds is lowered. That allows to more accurate determination of composition without distractions. So what it practically means? So if you do just regular TGA-IR measurements, so there is some components already evolved, and maybe they are starting to decompose just on fly. So you have pretty complex mixture. You have chunks of molecules. So if you would like to simplify it, go with a low pressure. That's will give you better, less complex mixture. So how it's technically done? A Bruker FTIR, we have TG interface and connected to the niche. Evolved gases from niche goes to the gas cell, which is at low pressure. So at low pressure, yeah, not talking, it's about maybe 100 millibar or so. So let's take a look on examples. Decomposition of glycerol. Just go with the regular ambient pressure. You can see we was able to identify composition, but composition is not simple. It's pretty complex. The carbon monoxide, dioxide, water vapor, formic acid, formaldehyde. So now we go with low pressure. This is just show the glycerol boiling point as a function of pressure. So you can see we can considerably reduce the boiling point by just going on smaller pressure. And now 60 millibar, so you can see decomposition, and that's much less complex compared to what we had before. So you can see reducing pressure allow you to better mixture analysis or better decomposition analysis. So now let's go to the practical example. For those who is doing, say, example, reverse engineering, we'd like to know what kind of plasticizers are used in the competitor product. We use a TG, and assuming that plasticizer evaporates or evolved first during decomposition. And then if you do it at regular ambient pressure, decomposition becomes pretty complex. Now what we can do, reduce pressure. So we reduce boiling point of a plasticizer. Run measurements at low pressure. And you can see that's in the red show that spectrum of something which is evolved from low pressure. And we can run against library search and can easily identify this is plasticized formalin. So if you do at regular pressure, so formalin start to decompose, and we see only chunks, and then actually we cannot solve this puzzle which plasticizer is used, because we just see only chunks of this molecule. So as you can see, hardware approach also allow to this low pressure approach allow you to better understanding what's going on with your sample, and simplifies all this analysis of evolved gases. So you can see that pressure variation offers an additional parameter for studying materials behavior. So in addition to the boiling point of evolved compounds is lowered, and therefore larger fragments are detected, and make very simple structural configurations. See, this is I will show you what kind of tricks and tips you can use to do this complex mixture analysis. And I would like just to, my last slide shows you what kind of instruments you can use from Bruker for couple with TGA-IR. The small one, you can use alpha, spectrum range mostly mid-IR. You can, the next step is the in vivo FTIR, which can be used not just for TG, but also for different types of experiments, including fast scan option, 50 spectra per second, and spectrum range can go from fine infrared to visible. And our flagman is Vertex ATV, which is go from terahertz to UV spectrum range, and you can do 88 spectra per second at 8-wave number resolution. It also can be coupled with FTIR. So you can see you have a lot of flavors over spectrometers to couple with NETCH TG. Thank you for your attention. I'm glad to answer all your questions.
Thank you for the presentation today. Now we'll be moving to a short Q&A session. If you haven't already done so, please submit your questions now via the questions drop-down box to the right of your screen. So we do have several questions already, so I'll begin. The first question is, how effective is atmospheric compensation correlation option available in OPUS?
Yeah, I can answer this question. So yes, it's very effective for compensation of atmospheric water in CO2 if you do regular measurements, but I certainly would not recommend it to do it for evolved gas analysis, because if you have water vapor involved during the gas analysis and you have atmospheric water vapor, and if you use this function, so it can actually reduce the spectrum of water which is evolved during analysis. So my recommendation, purge instrument very well before you do the measurements. And the most important to have a stable purge. So if purge does not change during your measurement, so that's you will not see atmospheric water in CO2.
Thank you, Sergey. Next question. Using the spectral library, can you quantify the gas composition, or do you need to run separate standards for that?
Yes.
This is Mike, and I can answer that. So for quantification of the gases, typically you'll need to know which gases that you want to quantify. And in order for you to convert the signals of the FTIR into a quantifiable amount, you will need a standard or a amount that you can measure either through TGA or a specific volume or quantity of gas. So this is the only way that you can correlate the actual signal and the signal intensities coming from the FTIR, and then convert that into a quantifiable amount in either volume or in mass quantity of the gas that you want.
Thank you, Mike. How much sample is needed to perform a TGA FTIR measurement?
So in order to generate, I would say, an adequate signal in the FTIR, it's really dependent on some of the conditions that you're running. So that might include the flow rates that you're using, as well as the gas atmosphere that you're running. So normally in these types of measurements, I try to target at least 1 to 2 milligrams of mass loss per step in order to acquire a very, very generous and good signal. If you use too much, you can oversaturate some of the signal. And if you use too little, you might not generate enough signal sensitivity.
Thank you for that. Is it possible to perform this kind of analysis with a DTGS detector on an Invenio R? If not, are other detectors available to be swapped in?
I can answer. So yes, it can be possible with a room temperature detector. So that's an example. We did such measurements with on edge TG with a small alpha FTIR, and small alpha used the TGS detector.
Great, thank you. We have another question, which is two questions actually. I'm familiar and a frequent user of TGA, but not familiar with FTIR. I'm considering purchasing an EGC such as FTIG, but I'm not sure yet. I have a couple of questions. The first question is, what are the different capabilities of FTIR versus QMS?
So the FTIR and QMS have a different type of acquisition in terms of the data that you're acquiring. So the FTIR looks at wave numbers, bond interactions, whereas QMS measures the mass numbers of the different molecules coming from your sample. So both of them have advantages and disadvantages. So one advantage of QMS is you'll get a mass number so that you can directly correlate to a specific type of molecule. So if, let's say, you have mass number 44, you can look up the different types of gases that produce mass numbers 44. So let's say carbon dioxide. Some of the disadvantages of QMS is that you may have overlaps in lots of different gas molecules produce the same mass numbers. And that's then where FTIR can assist in trying to interpret which types of molecules you're dealing with. So for example, mass number 28, you can have nitrogen or carbon monoxide. And with an FTIR, you'll be able to differentiate whether the 28 means it's nitrogen or whether it means carbon monoxide.
Great. And the second part to that question is, what is the output from FTIR test and how you translate it into gas identification that we can couple with TGA curves? The blue line, water, of the first presentation in the TGA, how the data from the FTIR was translated to that curve. It seems that the second presentation that the FTIR will give us the spectrum. How is the spectrum translated to the water curve and others? And is it an automatic process?
Yeah, I can answer this question. So yes, so when you got a spectrum, so you have a 3D file, which is first of all, you can look on the total changes in the spectra. It's called Gram-Schmidt. So it's very similar to TG curve. So you see, but in a spectroscopic sense of view. So it gives you total changes in the spectrum. But you also can, the beauty of FTIR and TG combinations, you can follow each individual compound, how it changes with temperature. So for example, you have water, you can take a look on the intensity of water bands versus temperature and make a plot. So it can be done automatically. And next, say CO and CO2, again, you can pick the band you would like to follow with temperature and take a look on this and behavior of this plot. So basically, you can actually see what actually goes on during the decomposition. Is it related, the peak on TG, is it related to CO2, water, any other compounds? You can easily plot all these gases intensity, band intensity versus temperature. So that's how that can be done automatically in software. And or you can just simply browse through different gases or different band position and take a look live what's going on with temperature.
Okay, thank you. We have another question. Could you please explain one more time the reduced pressure technique, how to create such a system, and what should I need?
Well, you need a pump. So, and then we have publications for this technique. So if you send me your in contact information, so I can send you all this publication we did. So that's explain details how it's done.
Thank you. I'm a new user to STA, F1, and FTIR. However, I have never been able to produce plots correlating specific mass loss stops from the STA to FTIR peaks as presented in a lot of your pictures in your website. Is there a tutorial that I can follow, as I believe that following the instructions from the manual is not enough to reproduce such plots?
So we could probably discuss this more offline, but one of the critical aspects is sort of your measurement conditions. So one thing I mentioned earlier is ensuring that you have the heated adapters so that you minimize and prevent condensation. So usually if you don't have correlating plots of the TGA curve versus the FTIR, it could be due to your gases condensing somewhere prior to reaching the FTIR, which creates a lag so that you might have offsetting curves in which you have a mass loss, but you're not seeing anything, but maybe you're seeing it much later in the plots. But we can definitely discuss this more offline for your specific unit and your specific experimental runs.
Thank you. Can you quantify evolved gases without TGA and FTIR?
Yeah, sure. Well, you can quantify it. So there is a few ways doing it. You need to know which gases you have in mixture, and you need to have a calibration set, which is basically you need to have a spectra, or at least couple spectra with known concentrations. And then after you make this calibration plot, so you can quantify these gases. And we also have a specialized gas analyzer, which is also based on FTIR techniques, and they use a specialized software which you don't need to make a calibration. So it uses published data measured with high resolution for making internal calibrations. So in this case, you can run your gases mixture from day one. You don't need a calibration, but that's our gas analyzers.
Which spectral libraries do you use?
I use two spectral libraries. One is coming from EPA NIST, so that's have about 5,000 gas compounds, and a smaller library, and we also have it's about 500 compounds. That's it's a public library, one of our national lab in the US.
So NETCH also has a polymer FTIR library. So as part of our TGA-FTIR coupling package, that is also an availability as well.
And what are the maximum number of components in your library search with the mixture analysis?
Yeah, that's the maximum number of components is 10. So, but I usually limit to 2-3 components, because if you select 10 components, and if they are very mixed together, so you'll not get satisfactory results. But in principle, if they're well separated, you can do this up to 10 components.
And does Bruker make gas analyzers?
Oh, you already mentioned, yes, Bruker make gas analyzers based on FTIR spectrometer, and they have a built-in calibration, so you don't need to use any additional calibration to use the spectrometers.
And does Bruker and NETCH provide training?
Yes, so I'm guessing we both provide training. I know for NETCH we do training for TGA STA systems, and also for evolved gas analysis.
Yeah, the good things about the broker and Netch, we are not only partners, but we are very close to each other. We are both in Massachusetts and about maybe like 5 miles from each other. So if you come for a training to a broker, you can visit Netch and opposite.
And is there any additional information that you can provide on the Opus software in detail? Where can I find that information?
Yeah, if you have an Opus software, so that Opus comes with a help file, so you can take a look on the help file. And if we also have a training course 4 times a year, so then you also are welcome to come for a training course. It's free. Nowadays we do it online, but if you have specific questions about TG, you can contact me or Mike directly.
Thank you. We'll just wait a little bit more time for some more questions to come in. If we have some, we'll just take a moment. Well, it seems that that's all the time we have today. If we were not able to answer your question here, we'll answer them directly to you by email. Please submit to either Sergey Shiloff at sergey.shiloff@bruker.com or Michael Su at michael.hsu@netzsch.com. The recording will be posted both on the Bruker and Netch websites for future viewing. And thank you very much for joining us today.
Thank you. Bye-bye.